So looks like there are a few people that are still sort of joining in. We'll go ahead and get started and let them join while we're already in progress. Today's webinar is on electricity, wiring diagrams, some troubleshooting techniques, and I found this presentation really tough to put together because there is a lot to talk about. I mean, we could easily do, a 5-part series on electrical troubleshooting, right? So there's a lot to go over and a lot to talk about. And so really with today, more than any of the the other 5 classes that we've done, I really would appreciate your feedback, right? So when we're done, you'll get a survey, and any any thoughts or suggestions or ideas or feedback on today's presentation would not only be helpful, but will help me make it better, right? So I just finished building this last night, I'm to blame for the content. So today, again, is part 5 of Wade's Words of Wisdom, or what my coworkers have been referring to as the most misleading webinar title ever. I don't know. I guess that's for you to decide, right? Again, as we always talk about in these classes, everybody that has come to all 5 webinars, if you've logged in and attended all 5 webinars, you'll get a free copy of the Ruud heat pump service manual. And there are a lot of great troubleshooting and diagnostic techniques with videos and great photographs and sort of step-by-step procedures to walk you through troubleshooting and diagnosing parts. There's also 4 prizes that we'll be giving away today, or that specifically Tropic Supply will be giving away today. This is a representation of some of those prizes or gifts. Each one of them will be valued at $50 or more. And the first person to answer each of 4 questions will win the prize. And the way that you're going to answer those questions, and I'll pause a minute before I ask the questions, is you're going to open up the chat window, which is down at the bottom of your screen where it says chat. So when we get ready, and any questions that you have throughout the presentation, ask them in the chat. Todd Sutherland is monitoring the chat window, and will answer any questions, anything he needs to toss to me. We'll just sort of do that as we go. And then at the end, we'll have a sort of a general Q&A session for anything that didn't come up or didn't get answered. So as I often like to do, we're going to start out with sort of the very basics and talk about electrical theory and atomic theory a little bit, because I think it really helps understand exactly what's happening when we have an electrical circuit, and in my mind that makes it easier when you're using your meter and you're testing. So we want to know exactly what we're looking for. But first, I'm not going to read through all of these warnings, but if you notice at the bottom of them, right, at the end of each bullet point, maybe not all of them, there is mentions of severe personal injury or death. So anytime you're working with any sort of electrical circuits, be careful, pay attention, don't stick your hands into a unit that is energized unless you realize it's energized and you're doing it on purpose. So just keep your head on a swivel. Right? In other words, electricity will kill you. So let's show it the respect that it deserves. Don't be afraid of it. But definitely pay attention to it and remember what you're doing. So all matter is made of atoms, and those atoms are made of three different parts, right? So the atom has a nucleus, which is made of protons and neutrons. And the protons have a positive charge, the neutrons have a neutral charge. And then the electrons orbit the nucleus, sort of like the planets in the solar system orbit the sun, right? They're not on a flat plane, sort of like the planets are, but they orbit, you know, in a sphere, right? In 360 degrees around that nucleus. And you can see here, I've got a sort of graphic representations or drawings of copper atoms. And on the very outside ring, that single atom, that single electron that's orbiting the nucleus in a copper atom, that electron is unstable. And they're referred to as free electrons. And substances that are conductors have free electrons or have an unstable outer ring. And materials that are insulators have a stable outer ring. So we can take these free electrons, right? That single electron on the outer ring of our copper atom, and we can push that electron, and we can push it or make it jump to the copper atom that's next to it. But when we do that, we're going to take the single free electron on that second copper ring, and we're going to push it to the third atom. And that's what we're doing, right? That when we are applying voltage, we're pushing those atoms, and they're leapfrogging from not pushing the atoms, we're pushing the electrons that are leapfrogging from atom to atom to atom. And the push that is required to do that is called electromotive force. Some people call it potential. And that's the push that makes the electrons flow. And that is voltage, making electrons flow, right? Pushing electrons from one atom to the next atom. And there's several ways we can do it, but the ways that we're going to talk about today are chemical. So we can create a battery, and that battery provides the electromotive force to push those electrons. Or we can do it magnetically, right, with an alternator, generator, or a transformer. And a transformer, in equipment that we're looking at, we can have a step up or a step down transformer. So we can take a transformer and we can use it to increase voltage or decrease voltage. We'll talk about transformers a little bit more here in just a minute. So I already mentioned voltage. What is voltage? So we all have a meter, right? And you're going to take your meter and you're going to turn it to volts AC or volts DC, and you're going to put your leads on and you're going to read your voltage. But what voltage is, again, it is the electromotive force that's pushing the electrons. It's very common and kind of easy to make parallels on the flow of electricity and compare that to the flow of water. So if we're going to do that, your voltage or your electromotive force would be your pump that's pushing the water. And we have either alternating current or direct current. Alternating current is abbreviated as VAC, volts alternating current. And what that means is that our current is going back and forth. So it's bouncing back and forth. And when you look at a light bulb, you think about the current or the voltage that's going through that bulb. It's not a constant. That bulb is power is passing through that bulb here in the US 60 times per second. So the voltage changes back and forth 60 times a second. That's 60 hertz. Internationally, a lot of countries use 50 hertz, and that's what that means. Or direct current, which is what we would pull from a battery, and that just moves in one single direction. does not bounce back and forth. So alternating or direct. And then we have current. Current is also referred to as amps or amperes. And the current is measured by the magnetic field that's created when those electrons jump from atom to atom across our conductor. And the higher the current, the stronger the magnetic field. So when you take your amp clamp, and you clamp it around a wire, it's measuring the intensity of the electromagnetic field that's being created by the current flowing through that wire. And so 1 amp is the current required to flow through a resistance of 1 ohm with a pressure of 1 volt. And I'm going to show you a graphic that I think will help to explain that here in just a second. And then resistance. Resistance is measured in ohms. And that's what that little omega symbol is there for. And 1 ohm is the resistance that will allow 1 amp to flow with a pressure of 1 volt. So voltage, current, and resistance are all directly related, and they all sort of affect one another. The higher the resistance, the higher the current, right? I'll show you again. I'll show you a graphic here in just a second. So current is equal to electromotive force divided by resistance, and that's Ohm's law. I have a Ohm's law graphic here in just a second. We're not going to spend a lot of time really talking about Ohm's law, but I want to use it as a graphic to just show you how everything's related, right? So this little cartoon here shows you your volt, or your electromotive force, or the push that makes the electrons flow, right? So that's our electromotive force. And the volt is what pushes the electrons. The amp, or the current, is the electrons flowing in any electrical circuit. And then the ohm is the resistance. Just like we talked about, I think it was 2 weeks ago when we talked about airflow, right? So your turbulence and duct design has a lot to do with the resistance of the air in the ducts, and that's sort of similar to resistance in a wire or your ohms. If you have a conductor or a wire that's undersized, it adds a lot of resistance. It's harder for the voltage to push the current through the wire. And if you have a really seriously undersized wire, that extra current also generates heat. And you can if you've ever wired, let's say 24 volt circuit accidentally to a 120 or 240 volt circuit, it bakes those wires pretty quick, and that has everything to do with the resistance and the current. Okay, so here's a couple of mathematical formulas. They're really all the same formula. We're just moving things around. And one thing that confuses folks about Ohm's law is just the initials that we're using, right? So current equals electromotive force divided by resistance, or volts. Amps equals volts divided by ohms. And you can see the sort of Ohm's law chart in any one of these characteristics that we want to solve for. We just need the other two, right? So E is volts, but that really comes from electromotive force. And I is current, and it's French. It really stands for, for intensity of current. I'm not going to try to pronounce that in French. So our amps is I for intensity of current. R is resistance. A lot of times refer to that as ohms, because that's how we're going to measure it. So an electrical circuit is the path of electron flow. So the path that the electrons take when we apply that electromotive force. And if you see in this graphic, we've got four things counting our conductor, right? So we've got our power source, which is a 120 volt wall receptacle. We have got a switch, which is our control, and then we have a load, which is a light bulb. And then the wire is our conductor that completes the circuit. So when that switch is turned on, the switch closes, and sometimes it's referred to as a closed switch, or it is referred to as a made switch. But when we close that switch, the current will flow through the switch and on through the conductor and through our load. When we turn the switch off, it is considered to be open or broken. And that doesn't mean that if we say it's broken, that doesn't necessarily mean that there's anything wrong with it. It's just a switch that is in the off position, or it's open and it's stopping the flow of those electrons.
Wade, I'm not sure if this is Wade, I'm not sure if this is a question or a statement, but somebody posted Ohm's law doesn't work on a capacitive load, only a resistive.
Yeah, that's true. But again, we're not going to really go into the details of Ohm's law. I just wanted to have the slide there to show that voltage, current, and amperage are have a direct relationship. So electrical circuits, we're going to talk about three different kinds of circuits, right? The simplest is a series circuit, right? So in a series circuit, we have a single path for the electrons to flow. And we have got a closed switch, we've got a motor, our electrons are moving through our closed switch, through the motor, which is our load, and then back to neutral. And 60 times a second, that power is going to reverse and it's going to sort of boomerang around, right? So back and forth. As long as we have our switch closed and we have electromotive force at L1 and neutral, then barring a mechanical failure of some sort with our load, the motor's going to run. And the next drawing is a parallel circuit, and you can see that we've got two motors. Each motor has its own access to power, right? So the motors are wired in parallel, but they're each wired in series with a single switch, right? So that open switch is wired in series with both motors, but the motors are wired in parallel to one another. If we had two loads on the same circuit, right, those motors are going to have to share that voltage. And typically, in what we're doing, we don't want that. And then we've got a series parallel circuit, which is a combination. So we have two motors. Each motor is wired in parallel. And then in series with each motor, we have a switch. Typically, in residential heating and air, typically our switches are either safeties or a thermostat, right? Typically, we've got low voltage switches. Our loads might be low voltage. It might be high line voltage. And we'll go over that here in just a minute. So we are going to talk about some wiring diagrams. We'll talk about two different kinds of diagrams, and then we're gonna sort of take those two diagrams and we're gonna put them all together, and that's called a factual diagram. So the first one we're gonna talk about is a schematic. A schematic is also called a ladder diagram. It shows you and identifies to you the electrical components. And it shows you sort of exactly how it works and how the loads and safety devices, switches and everything else, how they're all sort of work together. The pictorial diagram shows you the location or approximate location of the individual components. It also specifies what wire color is going to what device. You can see on the top right, our schematic diagram does not list any wire color, and everything is sort of very rigid. It's called a ladder diagram because you've got your power on the outsides, and then across in the middle where the rungs of the ladder would be are going to be your loads. The pictorial shows you, or will show you when you look at it on the diagram, will show you the same devices. It's just laid out differently. So one of them is sort of a road map, and then the other one is sort of a sequence of operation, if you will, right? So pictorial shows location and specifies color. Schematic illustrates how the unit works and how the electrical connections are made. These diagrams are all shown in the de-energized position. So anytime you're looking at a schematic or a wiring diagram, just know that it is showing you the position as everything is de-energized. And then the factual is a combination of both of those. And typically that's what you see. If you pull off the panel of one of our units, you're going to see a factual diagram. So this is a schematic for the components in the outdoor section, obviously, of an RA14. So here's an RA14. These are our loads and our switches and our safeties. And there's always a legend with a wiring diagram. Well, I shouldn't say always. There should always be a legend with a wiring diagram to let you know what's what. And some of these things are pretty obvious, right? Right there, that big circle in the middle, that's our compressor. Then below that, we've got an outdoor fan motor, a run capacitor, etc. So those dotted lines are represented by represent field wiring. So that's where our line voltage from the disconnect wires into our terminal block. And you can see it's showing us our contactor. And I can determine from looking at this drawing that the contactor that we have is a single pole. It's a double pole, sorry, single throw double pole contactor. We've got a open set of contacts between L3 and T3, and then we've got a brass bar between L1 and T1. We got our line voltage coming in, and then everything on the back side of the contactor, from the contactor to the loads, that's all called the load voltage. We got line voltage coming in, we got load voltage coming out. We can also look at this schematic diagram, and we can see that we have got some other switches, right? CHC is a crankcase heater control, and LAC is a low ambient control. And just from looking at the diagram, the symbols themselves, you can tell what type of switches these are. So if you look at on the crankcase heater control, on the top, you can see that red squiggly line, that designates that this is a temperature switch. So I know right away that this crankcase heater is the crankcase heater control is a thermostatic switch or a temperature switch. And I can also tell by the drawing that it opens on a rise in temperature. So you can see as that line goes across, on the right-hand side, it's on the top of that contact. So as the temperature increases, that crankcase heater is going to push that switch open, right? So it's an open on rise temperature switch.
Wade,
Yeah.
can you replace a single throw contactor with a double throw?
Well, can you? Yes. The reason that you don't, and the reason that a lot of times they're used in equipment, is because the single pole allows us to have electrical potential going through the windings in our compressor, and that does generate a little bit of heat. So a lot of times that's used as off-cycle crankcase heat. So I always recommend going back in with OEM parts and with the same type of device. But that's one of the reasons that a single pole contactor might be used. Okay, low ambient control. So the symbol at the bottom of the low ambient control, that little sort of half circle, indicates that that's a pressure switch. And the way that the contact is aligned with the bottom, the switch is lined up with the bottom of the contact on the right. That tells me that this low ambient control opens on a drop in temperature, because we can't push it up any higher, right? If we were to invert that and have that red line on the top of the switch contact, it would open on a rise in pressure. But just looking at it, I see that I've got a low pressure control and I've got a high temp control. And that's what these two symbols are telling me. So here, we've got the same schematic for our outdoor unit. And we've also, right, so we've got line voltage, and then I added the control voltage schematic to the bottom of it. So you can see we've got two completely different circuits. One on the top is line voltage, and then the one on the bottom is going to be our 24-volt control voltage schematic. Again, you can see our contactor is right here, but then on the bottom side of the drawing, our contactor coil. So when we energize the contactor coil, when we push 24 volts through the coil on that contactor creates an electromagnetic field, so it becomes a magnet, and it pulls the linkage down on our contactor that then closes our L3 to T3 contact. So we've got both low voltage on the bottom, high voltage on the top, but they are the same component, right? Contactors and relays, sequencers, right? There are a lot of components out there that have both high and low voltage components to them. But when you look at the schematic, they're going to be split up between your line voltage and your control voltage, your load voltage and your control voltage.
Wade, we have a question back on the low ambient control and the crankcase heater.
Mm-hmm.
If the low ambient control opens on a temperature drop, why is the symbol not the same as on the crankcase heater control? The symbol looks as a pressure control.
Okay, you're talking about the symbol itself?
I think so.
So the symbols are different because this low ambient control, it's a low ambient control, but it's based on pressure, not temperature. So it's not a temperature switch, it's a pressure switch. And the crankcase heater control is a temperature switch, and that's the difference between the two symbols. Whether it's an open on rise or a close on rise, it doesn't really matter. This squiggly line tells me temperature, and this half moon tells me pressure. And then what sort of designates whether it is open or, open on rise or closed on rise or what is how it's lined up with the contacts here on the switch. I hope that answered the question. Okay, and then why? So here, Y and Brown are from our thermostat. That's what that's called. Here's an example of a pictorial diagram, and on this pictorial diagram, you can see CC. That's still our contactor, and you can see that we've got L1, T1, L3, and T3. You can see that off of our contactor, we've got a red wire coming off of T3 that goes to the run terminal on our compressor. We got a black wire coming off of T1, and that goes to common on our compressor. And then we have an orange wire that also comes off of T3 going to the common terminal on our dual capacitor. So usually you'll want to look at both the schematic to see sort of how the voltage is flowing or how it should and how things are wired, but you're also going to want to look at the pictorial to see sort of a graphical representation of how they're wired and to know what color wire you're looking for and looking at. The diagrams will also show you optional devices. So you can see this, the dotted wire is for an optional component. And if we had the low ambient control, we would wire it from T1 off of our contactor through that low ambient control and then up to our outdoor fan motor. The schematic doesn't show that that part is optional, but the pictorial diagram does. So it's easy to waste a lot of time looking for a component that's not there. So make sure you check both the schematic and the pictorial when you start troubleshooting.
Wade, will we always have this wiring, or do you see that inverter boards are going to take over the industry?
Honestly, I don't know how long we can not use inverter technology, right? As the Department of Energy makes, increases efficiency, minimum efficiency ratings, there's only one way to do that I know of, and that's to use inverter technology. So I think it's a long way off before everything uses that. But at some point, yeah, but we're still going to need wiring diagrams because there's still going to be safeties. There's still going to be, other controls that are wired on that unit. So we're still going to need to know how to look at wiring. But yeah, I mean, inverter technology is here and it's only going to become more and more common, I believe. Okay, so you can see I drew a box around all these other optional controls, right? Crankcase heater control, high pressure, hot gas sensor, low pressure, etc. We've also got an optional start capacitor and start relay up top. And again, these are all showing wire color and whether that component was sort of stock or optional. And here's a factual diagram. So right on the right, we've got a schematic. On the left, we've got our factual diagram. And then along the bottom, we have our legend that shows component code, any notes, and what the wire color abbreviations mean. And all these diagrams you can find in My Ruud under PTS. So you go to that piece of equipment, you can either click wiring diagram or you can get the wiring diagrams from the installation manual. Either way, but they're all there. All right, so we are at our first quiz. Go ahead and open up your chat window and get ready to type. So our first question is, explain electromotive force. So what is electromotive force? And it can be a very simple answer, right? I'm not asking you to write a dissertation about electromotive force. Full disclosure, I am not an electrical engineer. And what I don't know about electricity, you could fill up the Grand Canyon probably.
So we have, this always cracks me up. All right, guys, got to slow down here a little bit. So we have a bunch of the first answers were voltage. And then we had push of electrons.
Yeah, I like that. Our next question is, which type of wiring diagram shows component location and specifies wire color?
Pictorial.
Correct. Any questions about those answers? Anybody throwing a flag on that, or
Thank you, A-Shock. He said I pronounced that close enough.
he's probably, you're used to that, right?
Yeah.
Okay, so now we're going to talk about components and symbols, and let me hide this control so that I can see what I'm doing. There we go. All right, so components and symbols. We talked about pressure switches just a moment ago. So here are on the left, we've got examples of pressure switches. And then in the middle, we have got examples of pressure switch icons, right? So the top pressure switch is a high pressure. It opens on a rise in pressure. Now, typically, the pressure switch itself will have some sort of writing or designation on that to tell you at what pressure that switch opens, and then again when it closes. It's the same for the low pressure. And you can see the pressure symbol is the same, but whether it opens on a rise or opens on a drop depends on how the actual contact or the switch itself is drawn, right? So the top switch opens on a rise in pressure, meaning as pressure pushes up, right? Pressure increases, that's going to push that switch open, is how I look at it. And on low pressure, as pressure drops, that symbol is going to pull that switch open. Temperature switches. This is an example of a limit switch. Now, the limit switches that we're looking at here, right? The top left and then that big black box on the bottom, those are normally closed switches. The graphic that I'm showing you, right, in the middle of the temperature switch, that is a normally open switch. So this switch is, depending on how we're using it, right, it's going to close on a drop in temp and then open again on a rise in temp. I know most of you on this call probably don't have a lot of regular dealings with gas furnaces, but just like the pressure switch will show you what pressures the switch opens and closes at, the limit switch from a furnace does the same thing. You can see I drew a little red box around where it says L150-20F. And what that tells us is that this switch opens at 150 degrees Fahrenheit and closes at 130. So the L150 is the open temperature minus 20 degrees. So when we hit open and we cool down 20 degrees from 150, the switch will close again at 130 degrees. That's what that means. If you have a furnace that's overheating, you're either overfiring the gas valve or you got airflow problems. Don't take a switch that opens at 150 and closes at 130 and replace it with a switch that opens at 200. Figure out why your switch is opening. I don't know, this is not an airflow class, but I think it bears repeating. All right, so our thermostat is also a temperature switch. It's actually a collection of switches, right? Some of them are manual switches, right, where you can turn the fan to auto or on, and some of them are temperature switches where we're either calling for cooling or calling for heat. And I know this is a super simple thermostat. And you can look on the drawing here. We can switch the system either from heat to cool. And our thermostatic switch, as the temperature rises, we're going to push that switch closed, and we're going to energize Y and G. Now, if we had the fan turned from auto to on, right there where it says fan auto on in the diagram, we would flip that switch up so that as long as the system is on, either heating or cooling, we're going to energize we're going to energize fan. Currently, the way it's set up is that we only get voltage to G when we have a call for Y, meaning that as the temperature rises, we push up on that switch, it closes, and then you can see we've got parallel circuits going to Y and G to our outdoor unit, or actually to our air handler and our outdoor unit, or our indoor unit and outdoor unit, I should say. All right, so contactors and relays, and I mentioned earlier that contactors and relays and sequencers and other components have both line voltage and low voltage, or line voltage and control voltage. And we're wiring our line voltage from our disconnect to L1 and L3. And then our load voltage is T1 and T3, and that's going to the loads in the piece of equipment. And then we've got our low voltage side, which is coming from our transformer through our thermostat to our outdoor unit. And that's going to energize that coil. So contactors and relays, they're really very similar. Typically, contactors have a higher rating, and they can handle more current and more voltage than a relay can. But it's all dependent on what we're working on, right? So you can see sort of at the bottom, the coil is really just that. It's a coil of copper wire. And when we send our control voltage through that copper wire, it creates a magnetic field that pulls this set of contacts closed. And in the off cycle, right, when we de-energize our coil, you can see right here, there's a spring at the top of this linkage, and this spring pulls the contacts back up. So we create a magnetic field by sending 24 volts through this coil. It turns it into an electromagnet, and that pulls this set of contacts closed. You can see here that the contacts are actually what opens and closes on the switch. And when the contacts are closed, that allows completes our circuit and allows power to pass through it. As contacts open and close repeatedly, they can become pitted. And if you look at the graphic on the bottom, you can see a pitted set of contacts and a nice new clean set of contacts. So as those contacts open and close, there's often a little arc that draws there. Anytime that arc is drawn across those contacts, it causes some pitting. And as those contacts become pitted, they have a higher resistance, meaning that it makes it harder for the power to get through. So when you're out and you're doing your maintenance, check voltage across your set of contacts on your contact. And you shouldn't really have a voltage drop across it. I mean, you might see 1 volt or a portion of a volt. But best case scenario, you really don't want to see any lost voltage across your set of contacts.
Wade, we got a couple of questions.
Yeah.
And one is, how come the contactors come installed upside down from the factory? I think what he's referring to is sometimes when the contactor's mounted on the panel of the condensing unit, that the load side is down, facing down instead of up, where if the line side was down, it's easier to run your wires into the unit and connect right to the line side. John, does that sound about right? Yes.
So I believe what happens in situations like that, and you probably find a situation where this is incorrect. But I believe what's happening there is the folks on the line have very specific instructions when they're putting these things together. We might have several different vendors, right, that we source contactors from. And if those guys on the line are told, or ladies, right, the people working the assembly line are told, when you pick up this contactor, make sure that the writing is right side up, right, so that you can read it. Well, we might have another vendor that places that sticker upside down, and that's one reason that it might be wired that way. It really, I mean, as far as voltage going through it, it doesn't matter. When it does matter is when it makes it more difficult to wire. And I understand where you're coming from. If you run into anything like that, and you feel it's a manufacturing error, let the folks from Tropic know what you found. Get a model and serial number and send it to them, and they'll forward it to me. But that's one of the reasons that can happen, is it's just we're using multiple suppliers.
And then Wade, we got another question. Why on the diagrams that you've been showing on the contactor is it listed as L1 and L3 and not L1 and L2?
That's just how we always list it. We're not going to see an L2 unless we have a 3-phase piece of equipment. So our drawings are always, for single phase, are always L1 and L3. As far as why, because that's the way we do it. I don't have a better answer than that. Any other questions?
Nope, that's it for now.
All right, so now we're going to move on to transformers. So a transformer is essentially two.
Sorry, Wade, real quick. A follow up on that is L1 and L3. Is that standard in the industry that you're going to see on most diagrams like that? Or will some manufacturers still use L1 and L2?
You know, they might. I can't really say. It's been a while, you know, since I've really looked at other wiring diagrams. I sort of have tunnel vision, you know, and I really am only looking at Ruud units and the way that we do it in years. There may be, but I'm sorry, I don't have a better answer for you than that.
Thank you.
So transformer is two coils, right? So we've got two electrically isolated coils, and they each one of these coils is wound around an iron core. And when voltage passes through our primary, it induces voltage in the secondary, and it does that through magnetic field. So our 120 volt primary coming into our transformer creates an inductive induces inductive power, meaning that we create a electromagnetic field, and that starts those electrons. That's the electromotive force that starts the electrons pushing on the 24 volt side, or our secondary. As I mentioned earlier, this would be considered a step down transformer, right? So we've got a 120 volt primary and a 24 volt secondary. But you can have step up or step down transformers, where you could have 120 volts coming in, and your secondary could be higher. It all has to do with how many windings around the primary and how many windings around the secondary. So we have a lot fewer loops on our 24 volt secondary than we do on a 120 volt primary. And then the symbol for the transformer is in the upper right. It's just the sort of half circles in the two lines between it. That's our transformer.
Wade,
Yeah.
two questions. Why does my contactor relay after the machine is off make a noise like is 24 volts excited?
There could be a voltage issue happening there.
I'm not sure if he means a contactor chatter.
Yeah, I think that's my interpretation, right? So if your contactor's chattering at any point, that means that it's not creating, your coil's not creating the electromagnetic field that it needs to pull that contactor and hold it down. Sometimes that can be because you have an undersized wire. It could be because your runs are too long. It could be because you have a couple of loose wire nuts. It could be because under a full load, say a heat pump, for example, where we've got several things going on at once, we could be having some trouble with that electromagnetic field.
And then on your last slide, I thought you said earlier that it was current, not voltage, that generates the field.
Yes, yes, it is. You're right. I should have said current through primary coil induces voltage / current in secondary.
And then a follow-up question to the previous comment asking if the contactor needs to be replaced. I think what Wade was saying is that you need to check all the voltage in the wiring first, not just condemn the contactor.
Yes, absolutely. So, there's a lot of things that can cause you to have a voltage drop. It could be that you've got an issue at the panel. You've got an issue with your wiring coming out to your unit. It could be like a lot of times pitting or voltage drop across a contactor. And I have some more slides about that here in just a second. It can be an ant got stuck in the linkage and the contactor's not closing all the way. And I've seen that cause one to chatter too. You get those little sugar ants. They really love the electromagnetic field that's created by the coil. And a lot of times they'll get in there and get crushed, but prevent you from having a really good closed switch. Okay, so we're going to talk about a little bit about the meter, and then we're going to sort of jump into some examples and troubleshooting exercises. So your meter measures the electrical characteristics of any circuit that you're looking at. And most of us have a multimeter, right? It's an example of a multimeter. It measures several different electrical characteristics. It can measure voltage, and it's going to do that by measuring the difference in the electromotive force between 2 points in the circuit. And it can either measure a voltage drop across a load, or it can measure electrical potential that's sitting there waiting to move. So when you're using your meter, you're either checking across a load, an energized contactor coil, a running motor, or you're checking across a switch to see if you have any potential or if you read any voltage drop across a switch. Now, there are a lot of other things that you can use your meter for, but the examples that we're gonna talk about today, you use that. And then we have an ammeter, which measures the strength of the magnetic field created by the current. And an ohm meter.
What's the difference between a 75 VA transformer and a 40 VA transformer? And don't say 35.
How much current it can handle, and how much load it's putting out. So I have a whole class that we could do on transformers, specifically transformers. and voltage drop and what they mean, and we can certainly schedule something like that. But if you are just replacing a 40 VA transformer with a 75 VA transformer, you might be causing problems, right? So you might think you're solving the problem at hand, but you might be causing some other issue downstream. And then so our ohm meter measures the resistance of a circuit or component, and we can use our ohm meter to find open circuit, or open component, or a direct short. And I don't think I had a slide of a direct short. So what a direct short is when we think about the path of the current in our electrical circuit, we've got a power source, we got a control, and we have a load. And if we have a completed circuit without having a load in there, that is called a short. And that short will send voltage right back to our whatever component it is, a board, a transformer, a breaker panel, and it'll cause an electrical short, and it'll blow a fuse, or it'll trip a breaker. So if we have a completed circuit, we have to have a load in there. We have to have something that is using that available power, or else that's what's referred to as a short or a short circuit. So here we've got a 24 volt electrical circuit. Very simple, right? We've got 24 volt. For some reason, my Alexa device thought that I was talking to her. So sorry about that. So we got 24 volts going through this contactor coil. And when we put our meter on either side of the coil, we can see that our voltage drop across that coil is 24 volts. If we open the switch, interrupt the circuit, right? We have interrupted the flow of electrons. So we check our voltage at our coil, and it's not there because our electrical potential is now sitting right here at the end of this switch, waiting for this switch to close. As soon as the switch closes, the electrons are going to continue to flow, and we'll have 24 volts at our coil. And so this is a very common misconception and a common mistake that people use when they're making when they're using their meter. If you check across an open switch, you should, when you check voltage across an open switch, if you're getting voltage there, that's telling you that the switch is open, right? And we're reading just 24 volt electrical potential, which is sitting right here. Once we close that switch, and the electrons are flowing through the switch, we shouldn't read any voltage because we don't have a load there, and we shouldn't see a voltage drop across that switch. Now, if we're reading across a switch and we see a volt and we read voltage, if I was reading 5 volts across this switch, when I go down and I measure across my contactor coil, you'll see that my voltage drop there would only be 19 because we're losing 5 volts here. We're not now, right? We have a really good set of contacts. We have a closed switch. We're reading 0 across our switch. A lot of times what people will do is they will read voltage in their thermostat, and they'll read from 2 terminals in their thermostat and think 24 volts means that switch is closed. It doesn't. It means that switch is open. 0 volts across a closed switch. You read voltage across an open switch. Which brings us to our contactor / relay, right? So on the top, we've got our low voltage. That's our contactor coil. On the bottom, we have got our set of contacts. And when we apply 24 volts to our contactor coil. That creates the magnetic field that closes L3 to T3. And so here we were talking about voltage and voltage drop. So we have no voltage issues. And I know I'm measuring in absolutes, right? Most of the time when you check your low voltage, it's not 24 volts. But when you check your line voltage, it's not, 230 or 240. They're not nice whole numbers. So we've got 240 volts coming in. But here in this example, we've only got 235 volts coming through on the load side of our contactor. So what that's telling me is that we have a 5-volt drop through the contactor, and that those terminals from the contacts from L3 to T3 probably have some pitting, or there's something going on that's causing me to not have a really good tight connection. The other way that you can measure that is just to measure directly from L3 to T3, and you can see that we have a 5-volt drop there. I would replace this contactor. Now, some much bigger contactors that can have handle much larger load and are more expensive, like motor starters and stuff like that, have rebuildable contacts and linkages. Your typical contactor for a residential piece of equipment does not.
Wade, is there a standard voltage drop that indicates replacement of the contactor?
So you really shouldn't see any voltage drop there. I know that the National Electric Code tells you that you shouldn't allow for any voltage drop more than 5%. What's going to happen though is if you're out there and you see that you've got a 5-volt drop, when you leave, that pitting or whatever's causing your voltage drop across that contactor or across that set of contacts is just going to continue to get worse. So on a good switch, you shouldn't really read any, maybe fractions of a volt. But as a best case scenario, if you've got contactors that have a drop across the contacts, you should replace them, or relays. And again, that could be because of pitted contacts or some debris in there, especially with older contactors that aren't sort of enclosed, right? Like an old school contactor that you can get to and see everything. There's all sorts of stuff that can end up inside a contactor that either makes the linkage not work smoothly or blocks the contacts from making good contact. All right, so now we have an outdoor unit that we're looking at. Thermostat is set for cooling. The outdoor unit's not running. We're going to go outside with our meter, and we're going to look to see, do we have power to our board, right? So we have 24 volts from our 24-volt red to common. So that's 24-volt hot to 24-volt common. We got 24 volts there, so now we're getting voltage at our board. So the next thing we're going to do is we're going to look and see, do we have a call for cooling from our indoor unit, right? So we have 24 volts to Y. Yeah, we do. So we're getting a call for cooling. So why is the unit not running? We check across our contactor coil. Are we getting 24 volt? Are we seeing a 24 volt drop across our contactor coil for those terminals? And in this example, no, we're not. So we have an open circuit. Now it says open coil circuit because right now it could be, right? We could be reading any safety or any switch or anything in the circuit that we're looking at. Circuit that we're looking at could be open and could be preventing us getting our power there.
Wade, on an earlier slide, it showed that you, on an open coil circuit there, you would read 24 volts, and on
Well,
a closed.
I might, as long as I had 24-volt potential sitting there at my coil, right? Let me sort of circle back to that, because that's a good point. So what we're going to do is we're going to use a method called hopscotching. And what that means is we're going to start at one end of our circuit, and we're going to sort of work towards the other end of it to verify where we have power and where we don't have power. Right, so here's our circuit. We're coming out of that Y terminal. We're going through a hot gas sensor. We're going through high pressure control. Then we're going through our contactor coil, and then we're coming back into CC in our board. Right, so we got a temperature sensor, we got a pressure sensor, and then we got our contactor coil. So are we getting 24 volts? Right, so we know when we, hang on, let me go back. We know when we checked across our contactor coil, we didn't have voltage sitting there. So what that tells me is there's no electrical potential at my coil. So I've got an issue somewhere with the power before it gets to my contactor coil. So what I'm going to do is I'm going to go and I'm going to start at Y, and I'm going to look across my first switch. Am I getting 24 volts through the hot gas sensor? And I read 24 volts. Yes, I am. So the contactor is not energized, but I've got 24 volt potential, right? I've got 24 volts of electromotive force through my hot gas switch. So I know that switch is closed. The next thing I'm going to do is I'm going to hopscotch to the next switch, which is our high pressure control. Am I getting 24 volts through the high pressure control? You can see that I've got 0 there. So I don't have 24 volts through my high pressure. And what that tells me is that that high pressure control is open. Because if you go back and look coming into that high pressure control, I've got 24 volts. So that switch is open. I've got 24 volts potential sitting there waiting for that pressure switch to close so that those electrons can continue to flow, go through my contactor coil, and then back to my contactor common on my board. Looks like I've got a duplicate slide in there. So there's another way that we could check this circuit to see which switch is open or what's causing us to have a problem there. We can check resistance on all these components, which is pretty commonly referred to ohming out the circuit or ohming out the switches, right? So I would say I'm going to ohm out my hot gas sensor. I'm going to ohm out my high pressure control. And then if I don't find anything weird, I'm going to ohm out my contactor coil. First thing you're going to do is you're going to switch your meter to read resistance or ohms. A lot of people use a continuity setting for this, where if the switch is closed, the meter beeps. That's fine. You can use it. You can use that setting as well. Again, we're going to check our hot gas, our high pressure, and our contactor coil. Those are our 3 loads. So first thing you got to do is you got to disconnect the terminals. Let me go back one slide. So there's 3 things that our meter is going to read when we're checking resistance or when we're ohming out a component. It's going to read OL, which is infinite or open. You can see right now we've got our meter. The leads are not touching. There is no complete circuit between our red lead and our black lead. This circuit is open. So your meter is going to read OL or infinite. Depending on what type of meter you have, it might show an infinity symbol, like a sideways 8. But typically it's going to show OL. It might show 0, which means that the switch is closed, but there is no measurable resistance across that switch, which is what we want to see. Or any number, which is going to be the voltage drop or the measurable resistance across that switch or component that you're testing. So we're going to disconnect the leads from our hot gas switch, and we're going to put our leads from our meter right there to each one of those connectors. You want to make sure when you're doing this that you don't sort of hold the connector and the lead with your fingers, because you can complete a circuit or show resistance across your body as you're as you're testing those, right? So if you've got your red lead in your terminal here and your black lead in your terminal here, you can get a false reading. So you want to make sure that you don't put you're not putting your fingers or your hands on your connector. Everything's de-energized. You're disconnecting these, and you're going to check across the switch. And we can see that we have 0 resistance. So our switch is closed, right? If it was open, it'd read OL. We have no measurable resistance, so that switch is good. We're going to do the same thing with the high pressure control. And on the high pressure control, it reads OL because it was open, right? Now, none of this is telling us that we have a bad pressure control. It's just telling us that pressure control is open. Why our high pressure control open? That's another topic for for another day. We may have a clogged condenser coil. We may have a refrigerant problem. But those are the 2 ways that we can check. We can either hopscotch to figure out which is the open switch, or we can disconnect those switches and we can check across each one and see what our resistance is. So I'm not going to go any further and check across my contactor, but I could. You would expect to see some resistance across your contactor coil. Typically, if you have a coil that fails, it's going to read OL. If you read resistance across your coil, it's probably good.
Isn't continuity easier for checking pressure switches?
I mean, it can be. It really just depends on how I learned to use my meter to just look at the resistance settings. But I mean, continuity will tell you because it'll beep if it's open or closed. What it won't tell you though is how much. Well, it will. Some meters will read out your own reading at the same time as beeping, and that's fine. You just want to look and see how much resistance you have, right? Because you have a switch that's been opening and closing, it could have built up some resistance, and it could be pitting, and that could be it could have. You could have pitted contacts in there, and that could be one reason that your relay is chattering, or your linkage of your contactor is chattering, because you got a voltage drop across that switch. So we talked about electrical theory. We talked about what makes those electrons hopscotch one another or bounce back and forth. And that's electromotive force. We talked about volts, amps, ohms, the 2 main types of diagrams, symbols and components. And then we also talked about some troubleshooting techniques. And again, this could be hours and hours and hours of electrical instruction. Okay, so open up your chat window, get ready for the 2 final questions in the final webinar of this series. So everybody ready? Question 3 is, what type of switch is this? This is an example of what type of switch. All right, so question number 4 is how many volts? What voltage would you expect to read across a closed switch? The switch is closed. How many volts are we going to read across a closed switch? 0. That is correct. We will read voltage across an open switch. We should not read voltage across a closed switch unless we are reading voltage drop, and we don't want to see that. Are there any other questions before we sign out or sign off?
No other questions. A lot of comments on that it was a great class. All right, thank you, everybody. Have a great